Hello everyone, this presentation is about selection sort and its real-world application. I'm Aameena Sana from CSE 4th semester's A section studying in Bangalore Institute of Technology. This presentation is a submission for my ADA Content Beyond Syllabus project. So without further ado, let's get started. So selection sort is basically an algorithm, a sorting algorithm. It's used to sort the elements into ascending or descending order. So we'll break down into how the algorithm works and the code and how the time complexity is derived, as well as we'll visualize the entire algorithm. So selection sort. The basic way selection sort works is we first find the minimum element of the entire array. We find the most minimum element and then we swap the minimum element with the first element. This is in the case of ascending order. So we swap the minimum element with the first element, and then we keep repeating this process until the entire array is sorted fully. So this is an in-place comparison algorithm, which basically means that the comparison is done in place, so it doesn't require any additional memory for comparison. So it's a very memory friendly algorithm. So this is the code for selection sort technique. This is the entire main function, a main logic of the selection sort, not the main function. So this is the function called selection sort, and then we pass two parameters to this function. One is the array itself, the unsorted array, and then this is the number of elements. So we uh, we iterate two loops, I loop and the j loop. The I loop begins from 0 to n minus 1, whereas the j loop goes from I plus 1 to n. The j loop goes from I plus 1 to n. And we compare if j is less than the minimum one. Minimum one is basically the first element right now. So if the jth element is smaller than the first element, then the first element and the jth element gets swapped, making the jth element come to the first place, which is the smallest element in case of ascending order. So this is the swapping logic. We use a temporary variable called temp, which holds the which is used for swapping. So here we swap the min index and I value, since I is greater than min index. And this is the main function where we directly pass the entire array. We are not taking the input from the user, we're directly passing the array. And n basically stores the size of array. Size of array is a function that's used to find the number of elements present in an array, this function. So array is this, and so it's basically used to find the number of elements in this array. And then we call the selection sort function and we pass array and n, number of elements and the array, unsorted array. And then we print f, sorted array, and we iterate in I loop to print the entire array, the entire sorted array. So let's take a look at the visual representation of selection sort. Let's say we have 64, 25, 12, 22 and 11. So as said in the algorithm, this becomes I, this becomes j. We compare I and j. We first run the I loop. The I loop basically finds the smallest element throughout the entire array. Which is the smallest element? Obviously 11 is our smallest element. So what we do, we bring 11 to the first position. We swap 11 with the min index. This is what we're doing here. So it becomes 11, 25, 12, 22 and 64. So this is what our first loop does. Now the second iteration. So our array looks somewhat like this right now: 11, 25, 12, 22, and 64. This is how our array looks right now. The second iteration basically leaves this entire element out because this is already sorted according to the ascending order. This is already sorted. This is the smallest element present in the entire array. So now we leave this entire element and we start from 25. Sorry, my bad. Start from 25. We go 12, 22, 64. Now we find the smallest element, which is 12. Obviously, very clearly it's 12. So 12 gets swapped with the first element. So this becomes the first element basically because this is gone. So this 25 becomes the first element. So now our array will somehow look like, it somewhat looks like this: 22 and 64. So this is how our array looks right now. And not to forget our 11 in the actual first place. So this is our final iteration would look somewhat like it's 11, 12, 22, 64, 25. Now we find 12 is done, 11 is done, 12 is done, 22 is also sorted. Now we have to compare. Now we're left with two elements, the last two elements. This, which is the smaller element out of 64 and 25. Obviously 25 is lesser than 64. So what do we do now? Swap. After swapping we get 11. Our array would look somewhat like 22, 25, and 64. Clearly this is our sorted array: 11, 12, 22, 25, and 64, ascending order sorted array. So this is the entire concept of how our selection sort works. This is a very rough calculation of the time complexity because, as you can see, I runs from 0 to n. You can call from 1 to n or 0 to n minus 1, one and the same thing. So our I loop runs from 1 to n and our j loop runs from I plus 1 to n, right? So I plus 1, we take I as 0, it becomes 1 to n. So they're both technically running from 1 to n, meaning, one second, meaning the first loop is running for n times, second loop is running for n number of times. So combined, they run for n squared times. So that's how we roughly calculate the time complexity within a few seconds instead of using formulas and instead of like calculating the exact time complexity. This is the rough analysis of time complexity. The proper analysis is done here. So the outer loop runs from 0 to n minus 2, which is n minus 1 time, obviously. And the inner loop, the total number of comparisons that we would get is n minus 1 plus n minus 2 plus n minus 2, which basically adds up to n into n minus 1 by 2, which is n squared minus n by 2, or you can write it as n squared by 2 minus n by 2. As we can see, n squared is bigger than n, so we don't include n while calculating the time complexity because n squared is much bigger than n, so we don't include n or n by 2. This entire thing is gone. Now 2 by 2 is obviously lesser than n squared, very less than n squared. We don't include by 2 as well, so n square is what the time complexity is when you calculate it by step. Real life applications for selection sort, manual sorting of small list. So for example, we have how humans sort a short list. For example, selecting the tiniest, smallest, lightest item from a bag, and then we select a little heavier item and then slightly heavier than that. So that's how we pick items from the bag, selection sort. And a system with very limited memory, since selection sort uses the in place sorting algorithm, so it doesn't require any additional memory. So it is very useful in the embedded systems or low memory environments where the space plays the highest priority than the speed. So selection sort is used in that case. And the third application would be when the number of swaps matter. So sometimes swapping becomes costly. When we're dealing with flash memory and all of that, swapping becomes really costly. So in that case, we use selection sort since it doesn't have a lot of swapping. It has one swapping method, that's it. When compared to like quick sort or other sorting techniques, there's like multiple sorts, multiple swaps. So that takes up a lot of that's costlier. So in conclusion, uh, simplicity is high. Selection sort is really simple, very easy to understand, and very easy to implement, making it like a really good educational purpose, or like for it's very useful for sorting small data sets. But efficiency, however, the time complexity, since we said it's big O of n square, yeah, since the time complexity is big O of n square, we can clearly tell that the input size matters a lot in this case. So as the number of inputs increases, the time complexity also increases because it's n squared, very obviously. So more number of elements, the sorting time would be more, making it not very efficient technique, but also like it's really simple for smaller data sets. So scalability issue, as said, it works better on smaller data sets than larger data sets, and alternative algorithms. So selection sort can be used for smaller data sets, but what if I have like a larger data set? So we can use techniques like quick sort and merge sort. They are like the alternative techniques, which is also like sorting techniques itself, but they are very efficient to sort larger data sets because the time complexity is bigger of n log n, which is much smaller than n square, obviously. So it doesn't take that much of time to sort. So that is it from me. I'm Aameena Sana. I'm from CSE 4th semester A section, studying in Bangalore Institute of Technology, and this was my presentation on selection sort and its real-world application, and deriving the time complexity, explaining the code, and also visualizing the entire algorithm step by step. Thank you.